Hey everyone, I'm Alice. Um, I do open source stuff. I work in Tokio. I work for Rust and the Linux kernel at Google. But that's not what we're talking about today. Today, we're talking about thread safety. And this talk is really about a pet peeve of mine and the way that the send and sync traits are usually defined. Okay, so that's going to be the topic. Yeah. So maybe it's not entirely true that it's not about ownership, but I think ownership is not the whole story. So what's the goal of this talk? I want to talk a little bit about why is the standard definition of send incomplete. I want to give you a different definition of send and sync, which is much more complete, and it should be a definition you can use even in the tricky cases. So just a little intro here. So why send and sync? Like, why does the Rust language have these traits in the first place? I mean, so the problem has to do with when we're dealing with thread safety. Well, if you have the same object, then, for example, if two threads write to the same object at the same time, then if you are not careful, then you can run into problems. And there are many examples of this, but this is the idea. So we need to somehow control access when several threads want to use the same variable. So what's the traditional definition? The traditional definition is that a type is sent if you can take a value and send it to a different thread. That's the traditional definition. But I think that there are cases where it's not really so clear, right? So the first one is going to be the mutex. So with a mutex, the way it works is that you have this function called lock, which, let's say a lot of threads call lock at the same time, then the mutex will pick one of them and give permission to that thread. And then the thread can use the value for some time, and then it gives up the permission, and then another thread can take over. So by introducing sleeps in this way, a mutex ensures that only one thread is using the value at the time. So there's no parallelism. So the lock function is generally only safe to use when the value is sent. So that must mean that this locking involves some sort of ownership transfer, right? So for example, thread 1 calls lock, does some stuff, and unlocks it. Then 10 seconds go by, and another thread does the same. So did we transfer ownership from thread 1 to thread 2? Well, sort of, but I mean, what happened during these, like, where did the ownership go during these 10 seconds? It's not really clear. I mean, maybe you say, oh, the ownership went into the either whatever, like nobody owns it for the 10 seconds, so actually we transfer ownership to nothing, and then later we transfer ownership from nothing to the thread. Okay, so you can kind of make it work. All right. Another thing that's kind of curious here is that there's not actually a move operation anywhere in this example. Like if you go look at the implementation of a mutex, like there's no move anywhere here. So even though we can sort of talk about transferring ownership in like, what do you call it? Like in an informal sense, there's no like line of Rust code that says, now I'm transferring ownership. So what's going on? So what about Arc? So this is another example. So atomic reference counts, that's what Arc means. The idea is that you have this value, and you have a counter for how many things have a copy of the value. And then every time you call clone, you get a new copy to the same value, and you increment the counter. That's the idea. And this way, you know that when everybody has stopped using it, the counter goes to 0, and then you can destroy it. So this means that you might create an arc that wraps some value on one thread. Then you make a bunch of clones to a bunch of different threads. And then at some point you begin to drop them, and then the last one gets dropped on thread B. So here, some sort of ownership transfer happened from thread A to thread B. But we again have this situation where, for one, like what happened while it was owned by many. So I guess we have some sort of shared ownership. So now we have to add that to our definition. Yeah. And it's also like, so I guess now, like the actual line of code that performs the ownership transfer, that's when we decrement an integer. So the reason I'm unhappy with the standard definition is that if you begin to think about it, every synchronization primitive out there becomes a special case in your rules. With the mutex, you say, oh, the ownership transfer happens in these lock calls. With the arc, you say, oh, the ownership transfer happens when the integer is modified and so on. But this makes it kind of tricky, right? What if you're going to write your own mutex? Then at this point, it begins to become kind of circular. If, yeah. So how do you know that your own mutex implementation is right? So what I would like is, I want a definition that tells us what are the rules in terms of like actual lines of code that perform actual operations on the value. That's the kind of definition I want. So here's my definition. So the idea is, send is really about mutable access. So the idea is, if you can perform mutable access from a thread other than the one the value was created at, then it's sent. And here, mutable access includes stuff like moving the value and destroying the value. And then sync becomes similar. Sync is when you are allowed to do immutable access from several threads in parallel. This one is, the standard definition is a lot closer to this than this with send. So I think my pet peeve is more with send than with sync, even though I think sync is rarely explained super well. So here's a table. Just to perhaps help with the understanding of these definitions. So there are two traits, so we have 4 options. The first option is that we don't have any of the 2 traits. It's not send, it's not sync. Or maybe it's just send. It's also possible that it's not send, but it is sync. And this is possible even if it's rare. And of course it can be both, which is the most common case. So the first thing is, if you're just accessing the value on the thread it was created on, then there's no thread safety problems at all, so it's always okay. And then we have send, which is mutable access from other threads than the one it was created on, which that's just the 2 columns where you have send. So this one is, that's by my definition. And the same here, immutable access from several threads in parallel, that's sync. But there's a weird combined case, which is, what if I want to do immutable access, but I only want to do it from one thread at a time? So there's no parallelism. In this case, send is okay or sync is okay. So you need one of them, but either one is okay. And the final case is mutable access from several threads in parallel. This is never allowed. So just to complete the table. Okay, let's go through some examples. The string type, like there's nothing that like whether you access a string on one thread or another, that's no problem. Like which thread you're accessing it on, it doesn't matter where you created it. So yeah, that's fine. Reading in parallel is also okay. There's no problem with that. You're just reading, no problem. You can only write to a string from one thread at a time, but that's just the bottom case here. So that's also okay. So string types and other things that are just plain old data, they're send and sync. Great. What about mutex? So this is kind of curious, right? Because if you look at the documentation, then log takes ampersand self. And this means that you only need immutable access to call log. But when you do that, you get mutable access to the value inside it. And so this is how the mutex is able to allow many threads to access the value by having log take immutable access. Anyways, how does this relate to the traits? Well, when you call log, you only have immutable access, and there could be many people who call it at the same time, but we only allow mutable access. But this gives you permission to do mutable access, but because the log call will use sleeping to make sure that there's only one thread at the time, then this is okay. So this means that sync, which corresponds to are you allowed to immutably access the mutex, is the same as send permissions on the inner value. And note that there's no way to get parallel access to the value inside the mutex, so it doesn't actually matter whether the value inside is sync. It's not relevant to a mutex. Okay? Read-write log. This is like a mutex, but there's another function called read where many threads can call read, and then they can all get immutable access at the same time. So in this case, immutable access to the read-write log can actually give you, well, parallel immutable access to the read-write log can also give you parallel immutable access to the inner value, but it can also give you the mutable access. So you actually need the inner type to be both send and sync before the read-write log can sync. So this is an interesting difference between mutex and read-write log. Immutable references. Obviously, like with an immutable reference, you're not gonna get mutable access to the value inside it. So it doesn't matter whether the value inside it is sent. That's completely irrelevant. However, because you can take a reference and then clone it, now you have two references, and then you can send one reference to another thread. By doing this maneuver, you're actually able to get multiple threads that have immutable access at the same time, even though you only performed a send operation. You didn't actually perform. So this means that immutable references, they're only sent if the inner value is sync. Okay? Mutable references, they cannot be cloned. So you only ever have one. So this means that mutable access gives you mutable access. Immutable access only gives you immutable access. So mutable references have the same traits. We already talked about Arc. Let's do it again. So an atomic reference count, it works exactly like the immutable reference from before in the sense that you can clone it. And now you have several things that let you access the same value. And so you can move them to other threads. So this means that you need the inner type to be sync before an arc can be sent. However, arcs also let you actually move the value. For example, the destructor could run on a different thread if the last arc is dropped on a different thread. So you need both send and sync. RC, this is like arc, but here, so in arc, this counter of how many clones there are, they do some special stuff to make it okay to modify the counter for many threads in parallel. With RC, as a performance optimization, they don't do this. But this means that having two threads calling clone at the same time, that's a problem. So therefore, an RC cannot be sync, but it also cannot be sent because of this cloning thing, where you can clone the value and send it, and then now you have shared access. Okay? I think something went wrong. Let me just find the right documentation. Okay, so cell, you might remember that the mutex had this thing where you only need immutable access to modify the value. And cell and ref cell, these are the same thing. This says ampersand self, but it still allows you to modify the value. And if we allow you to do this from several threads in parallel, then we have a problem. So cells are not sync. But it's still sent. Because with send, you only access it from one thread at a time, and even if the access is immutable, and as long as you do that, it's fine. Now here's a curious example. So mutex guard is sync, but it's not sent. And the reason is, so in the implementation of mutex, there's some unsafe code, and if you destroy the mutex guard, that's when you give up permission to access the value. If you do that on a different thread than where you created it, then this unsafe code does some incorrect stuff. And so because of this, it cannot be sent. But sync is not a problem because sync just allows you to immutably access the value inside it. And so it doesn't actually give you any. And so sync is fine. And this is how we end up with this not send but sync situation. And this one is very interesting as well. There's a crate called sync wrapper. If you have mutable access to a sync wrapper, then that's the same as mutable access to the inner value. But if you have immutable access to a sync wrapper, then it doesn't have any single function that allows you to modify it. So this means that you could just do nothing. And it turns out that doing nothing in parallel is okay. So it's always sync, even if the value inside it is not thread safe at all. And this one, when I found out about this, I was really surprised. So immutable global variables, of course, they allow you to do immutable access in parallel, and they never allow mutable access. But actually, this means that globals require the type to be sync, but it does not need to be sent. So you can actually have a global with a value that's not sent in it. I don't know, that surprised me. Yeah. That was what I had.
How do you implement the mutex lock function without modifying internal states of the mutex?
How you implement a mutex lock without modifying?
Yeah, because lock only takes the immutable reference itself.
So the answer is that it does modify the internal state. So generally, modifying stuff with immutable references. This is also what we saw with cell and ref cell. Like, this is okay as long as you don't trigger problems if people call you in parallel. And so what mutex does is, well, it does many things, but part of what it does is that it uses atomic integers, which are these special instructions that the CPU has that allow you to have several threads modify the number at the same time. And by using these atomic instructions, it's actually okay to modify the integer, even though you only have immutable access. So it's not really immutable.
How is that represented in the language?
How it's represented in language? Well, one way you could define it is that mutable references is actually when you have exclusive access, when there's only one thing accessing it. And that also matches the table we had before. The bottom row here, that's because mutable references are exclusive, so there's just never any situation where you can have several of them. But one way to define immutable references is as shared access. And so immutable references, well, if it's really shared access, the question is, okay, can I modify this thing? Well, if you can do it in a way where the modification is okay, even if there's shared access, then it's okay. And so in the case of atomics, it does it using these special CPU instructions, or in the case of cell, they do it by not having sync. So even though it's shared, there's only one thread.
Could it be that your pet peeve with send is actually a pet peeve with the definition of ownership? Because the ownership concept doesn't cover the heap, because the language itself does not really know about it.
Perhaps. I mean, I think really my pet peeve is that I want the definition to be in terms of operations that actually, in the language, operations you perform on the value. And I guess you could say that, ownership is just when you do mutable stuff. But I don't know, it doesn't really feel like an intuitive definition.
Because when you say value, I guess you're thinking about value on heap, right?
Well, it could be on the heap.
When the arc is wrapped.
Yeah, it could be on the stack.
From kind of the perspective of Rust as a language, that thing is not really a value at all. Like you can't preference, like you can't have a variable can never refer to something like a heap.
I mean, you can have a reference to it.
Yeah.
Yeah, I mean, I don't know, I think this becomes a question of semantics. But I do really think that there's something about, like, if you want to make the ownership definition work, then you have to define ownership as performing mutable actions. So isn't it better to just say, send is about performing mutable actions instead of going through this extra route?
You've given some excellent new definitions of send and sync. Maybe do you have a suggestion for if we could change the standard library and name them something else? What would be the name that I call something that is send?
Ah.
I don't put it on
Naming things, yay.
I mean, so perhaps one way to talk about it is that send is really about, is it locked to one thread, right? I don't know. My pet peeve was not with my pet peeve was not really with the name, it's more with the definition. I mean, the definition and the name kind of, they make sense as a pair, but I don't know. Yeah, it's a difficult question. Naming is hard.
Does your definition not break down a bit if you think about things that are sent, that are not sent, not because of the access that allows to it, but because it uses thread local storage or similar.
But that's kind of similar to the mutex guard, right?
Yeah. But it's not because of the type of access that is allowed to it, but more because that it cannot be moved to another thread because of the same reason with the mutex guard.
I mean, the problem with the mutex guard is that there's an operation you're not allowed to perform on threads other than the valued thread that was created on, specifically because of some thread local stuff, and that's this one.
Yeah.
And so the fact that you're not allowed to perform this operation on threads other than the one it was created on, that's why it's not sent. So actually, I think it makes sense.
Yeah. It's just a very wide definition of mutable access, I think. But yeah.
Yeah, but you do have to include these in mutable access.
Yeah.
Maybe that I didn't quite understand it, but you mentioned a library called sync wrapper, which is sync, I assume, and allows mutable access. If you have a mutable reference, it allows mutable access. That sounds to me like it would be in the bottom column of the table, right? That you just have data rates.
But so if you have mutable access to the sync wrapper, if you have that, then you know that there's only one thread at the time, because that's just how mutable access is. Does it make sense? Because we only have one. Yeah, so this is just because of the normal guarantees of mutable references that there's only one. So it's just a function that literally takes a mutable reference to the sync wrapper and returns a mutable reference to the contents. Any more questions? No? Thank you.